Hello and welcome to this GibbsCAM Tech Tip. In this video, we'll take a look at programming tangent barrel mills to achieve better surface finishes while using larger stepovers in 5-axis toolpath. As you probably know, when you're surfacing in 3D or 5-axis, taking multiple strokes to finish complex shapes that can't be cut with the flat end or the edge of a standard end mill, the larger the radius of the tool at the point of contact, the better the surface finish will be given the same stepover. This also means that by using a tool with a larger radius, you can make larger stepovers and maintain the same cusp or ridge height. Let me show you what I mean. If I create a surfacing process with a 1/4-inch ball mill and shoot for a 50 millionths ridge height, I would have to take 7,000 stepovers along the surface to achieve that ridge height. If we change the end mill diameter to a 1/2 inch and recalculate, we can step over 10 thousandths with this tool and maintain the same ridge height. Now, for the fun of it, let's change the tool to something absurd, like a 7-inch diameter ball mill, and recalculate. Here we would be looking at a stepover of about 37.5 thousandths. This tool would only require about 1/5 the number of passes that the 1/4-inch ball mill requires to achieve the same ridge height. And there would be about 1/5 the number of ridges. And because there are significantly fewer ridges, you might find that you could actually step over even further and maintain the effective surface finish that you need. But really, who wants to pay for a 7-inch diameter ball mill to machine this surface? Even if we could, in this case, we wouldn't be able to reach much of the surface at all without gouging the floor with that large of a tool. On top of that, with a 7-inch diameter tool, we'd lose so much spindle speed and therefore actual feed rate in maintaining a reasonable surface speed. But wouldn't it be nice if we could gain the advantages of creating the finish and stepovers of a 7-inch ball mill while maintaining the spindle speed of, say, a 3/4-inch diameter tool and still be able to get into tight corners like I could with a 1/4-inch ball mill? Well, coincidentally, that's why we're here. There's a tool called a tangent barrel mill, or sometimes called a tangent mill. Regardless of what you call it, it can achieve these goals. So let's take a look at how we set it up. This is the tool profile selection for a tangent barrel mill. We have the diameter and flute length, of course. We also have a main radius and a tip radius. If we have a tool with a main radius of 3.5 inches, we can use the same stepover values we would with the 7-inch ball mill, but our spindle speed in this case is calculated for the actual 3/4-inch tool diameter. And this tool also has a ball end. In this case, the tip is essentially a 1/4-inch ball mill. So with this tool, while we're cutting with the main 3.5-inch radius, we can take those 37.5 thousandth stepovers and still maintain that 50 millionths ridge height, stepping over as though we were using a 7-inch ball mill. And our spindle speed will be for a 3/4-inch tool diameter, and we're still able to reach into 1/8-inch radius corners. So let's create some toolpath with this. Now I have a stock model with some material remaining, and I've already finished the floor with a flat end mill and the fillet with the ball portion of our tangent barrel mill, so that we can focus on creating toolpath for finishing the wall of this part. I'll create a 5-axis toolpath with our tangent barrel mill and reset the defaults, which is often a good idea before creating new toolpaths. And I'll set my speeds and feeds, and then we'll take a look at the surface paths page. I'll keep this simple and use a morph between two curves. Now, I've gotten more and more into the habit of making features out of the selections I know that I'll be using, even on relatively simple parts. So I'll have the feature manager open, and I'll define my drive surfaces, my first edit curve, and my second edit curve. I'll go ahead and add a little extension to the strokes, something I like to do in situations like this, where the toolpath is running right exactly to the edge of the part. I want my toolpath to run one way, climb milling, and we'll define the step over at 37.5 thousandths. Now, looking at how we want to control the tool axis, I want the tool axis to be tilted relative to the cutting direction. But in this case, I don't want a fixed side tilt angle. I want to control my side tilt by the contact point. And I prefer to define the contact point by line parameter rather than by the distance from the tip of the tool in this case. And I'll explain line parameter in just a minute. And the section of the tool profile that I want to be considered or looked at or used for this toolpath is set here in this drop-down menu. I'll open the tool page up again to help explain what these options are. Full profile considers or uses the full cutting profile of the tool from the very tip of the tool here to the top of the flutes here. The next option, curved profile, considers the curved portion of the tool profile from the tip of the tool to the top of the large radius along in here, but does not include the straight portion of the flute, if any. Barrel, on this type of tool, considers only the large radius of the tool, in this case the 3.5-inch radius. And cylinder considers only the straight portion of the flute, if any. For this cut, we'll use the barrel selection to make sure we are cutting with the 3.5-inch radius. Now we get to line parameter. Line parameter is the method I selected a minute ago to define the contact point on the portion of the tool that we said that we're using, in this case the barrel or the 3.5-inch radius. The line parameter is a value between 0 and 1 that represents the percentage of the distance from the lowest point on the portion of the tool that we're using, the barrel, with 0 defining the lowest point and 1 defining the highest point. So if we were to enter 0.5 as the line parameter, the contact point would be 50% or halfway along the 3.5-inch radius on the tool. If we check this box, we can create a range where the contact point starts out using this value and shifts with each pass so that on the final stroke it's using this value. So we're changing our contact point with each pass or each stroke that occurs. I'll set the cut to start at 0.9 or 90% up in this area at the beginning of the cut, and smoothly transition to 0.1 or 10% in this area by the time it reaches the bottom of the cut. For gouge checking, I'll check the floor and the fillet, retracting along the tool axis if needed. Now we need to deal with the link tab. This is where we control the behavior of repositioning moves. Basically, toolpath moves that aren't cutting. This could include lead-ins and outs, step-overs, moving to the start of the next stroke, or moving to a new area, things like that. The first thing I'll do is specify a lead-in for the initial entry and a lead-out for the final exit. And I'll have the tool stay on the surface for any small repositioning moves. On the large moves, I'm going to specify retracting only to the rapid distance, which I will define shortly. And since I'll be cutting in one direction, I'll specify a lead-in out for these moves, which will be when it moves from the end of one stroke to the beginning of the next stroke across the part, since I'm climb milling each stroke. On the retracts page, I'll reduce the clearance area height to 4 inches as well as the incremental clearance plane, just to keep things a little tighter since I'm not expecting a lot of rotation here. I'll make the rapid distance a 1/2 inch, which is where I have it set to move between each stroke, and the feed distance to 1/4 inch. Keep in mind that these are incremental values, so we're not going to be clearing the top of the part for these repositioning moves. So we need to make sure that our lead ins and lead outs will get the tool clear of the front of the part between strokes. I need to hit OK, and now take a look at the default lead in and out. In this case, I'll reduce the arc sweep to 45 degrees and the arc diameter as a percentage of tool diameter to 100%. I'll copy this over to the lead out, hit OK, and go ahead and create the tool path. That looks pretty good to me. Some might choose or prefer to go back and forth to eliminate the retracts, and that would be fine. But generally, when surface finish is a primary concern, and with these tools, it's typically more common to climb mill each stroke. Once you're comfortable with this type of tool path, if you want to minimize repositioning moves, you may decide to go back to the retracts page, under the link tab, and set the rapid distance and the feed distance to 0. Doing this, you'll want to make sure that the air move safety distance will prevent the tool from rubbing any floor. I'll have it come up to 100 thousandths incrementally. Hit OK and redo. You can see that this really minimizes the retract motion on these repositioning moves, but it requires that the programmer be very diligent in ensuring that the tool motion is safe and doesn't contact the part at any point during the rapid move. And here we go. As you can see, even with a relatively large step down, we have a superb surface finish requiring far fewer passes than would be required with any reasonable ball mill. Plus, we'll finish all the way to the fillet with a single tool, something that if we used a traditional ball mill would have required a 1/4 inch or smaller tool and at the very least 5 times the number of passes. In this video, we explored using GibbsCAM's 5-axis module to very effectively use a tangent barrel mill to improve surface finishes while greatly reducing the number of passes required, all without sacrificing spindle speed and allowing us to access smaller inside corners. These cuts are easy to set up once you understand how to control the contact point and are very effective in improving part quality while reducing cycle time. Effective use of tangent barrel mills can be a powerful addition to your 5-axis arsenal of tool paths. If you would like more information about using tangent barrel mills or any of the many other ways that GibbsCAM can help you improve part quality and reduce cycle times, reach out to your local reseller.